Okay, so welcome back to another StackLang episode. And in this one, we are going to implement if statements because we need some conditionals for our language because otherwise it's kind of useless, right? It's not really Turing complete, right? If you don't have if statements. So yeah, like jump labels and stuff. So let's take a look at the repo, right? And first things first, let me just show you some things that I added, right? So that's pretty interesting, I would say. And yeah, I mean, the language doesn't look different, right? I was experimenting with what if you name your function like some weird random characters like this. Imagine that. That's, I mean, something really cool to be able to create your own operators. I mean, I haven't tested if it works with emojis though. That's next. I mean, Mojo doesn't have shit on us, basically. That's what I'm gonna try to say. So if we try to compile, yeah, I forgot about that. Yeah, Mojo still, it's Mojo, right? Like Mojo language, that piece of shit. Yeah, okay. Anyway, so we could add support for emojis. It's pretty easy, to be honest. But yeah, let's just see what I added, right? So first of all, comments are, I think we saw comments last time or something, but I added true, false. These are booleans. But if we run this thing, you'll see that a boolean is a 1, or like true is a 1 and false is a 0, right? And you would say, okay, and how do you represent these things in the memory, right? That could be interesting, right? It's gonna be 1 byte, or how is it implemented? Let's search for boolean. Okay, yeah, I mean, I wanted to search for bool or some. Yeah, sure, fair enough, fair enough. It's making fun of me. Okay, so yeah, this part, right? So you think that it's different than int, but it's actually the same data structure as the integer. So why do we allocate 8 bytes, right, for a boolean that only is 1 or 0? Well, I want the stack, or I guess in this case it's the heap, because the stack will always be just uh, words on the stack, right? Only pointers. But on the heap, you could put pretty much anything, right? But I'd like it to be 8 bytes aligned, so we don't have any problems in the future when we add strings, for example. They are gonna be 8 bytes aligned, so it's gonna make our lives a bit easier if we assume that everything is divisible by 8 on the heap. So that's the idea. And the other thing that I added is the greater than, less than, and equals operators for integers, obviously. So if you say 10 10 equals, it's gonna return a boolean, which is 1, right? And if you say, well, we don't have not equals. That's interesting, right? We don't have not equals, but we could add it, right? But it doesn't matter. So if you put greater than, and it tries to compare, this is the first argument, this is the second one, it doesn't work. But if you do like 13, it's gonna be true, right? So we have these operators for now, and we can implement maybe if statements using them. And yeah, how these work, right? I just looked into the cool compiler, like the previous language that we did, and try to copy paste this idea. So if you remember from addition or the other operators, we use RAX and RDI, right? So RDI is the first argument and RAX is the second one. So if we call to this compare instruction, Then we use the set G, which I think it's setting like a bit in AL. If the comparison was resulted in greater than, so RDI was greater than RAX, then we set G. Then we make sure that it's only gonna be a 1 or 0. If we do the AND, that's gonna happen, right? We set the 1 bit, and or I guess the 0 bit, the first one, and then we move 0 extended, and that means that we set everything to 0 in RX, and then we put the 1 or the 0 from AL into the lower register of RX. So yeah, then if we call to the constructor of the boolean, it's gonna do just the same as the integer. It's gonna allocate this value on the heap and put a pointer on our stack. So if we pop it, yeah, we get the value. So less than, it's just set L, and you have to make sure you don't use set LE. LE is less than or equal, right? And then EQ is just set E. I think you can use test instead of compare for equals, but yeah, I think it's fine. Okay, and the other thing that I did, yeah, this part I hate it really badly, but the other part that I did was, if you remember, I said at some point that I don't really like that we use the function names that the user provides in assembly directly. So I wanted to have a convention that we convert function names into some kind of other label, and then use that label in assembly and maybe add a comment with the user function name, right? So that convention is going to be basically, we take the function is in order, and we just say this is function 1, function 2, and so on. So if we take a look at example.asm, you'll see that functions are going to be function 0, function 19, because you cannot have, like, this isn't valid assembly, right? So we needed a way to map from the user functions to our own functions. Yeah, that's kind of what I did, but we have, like, pretty much everywhere in our code, right, we use string slices, right? And these string slices are gonna be, let's just say, so where is one example? Okay, yeah, node value. So this is, I mean, I guess a value doesn't really matter, but maybe this one is a better example, right? We use a node value. Actually, this value, like the string slice, comes straight from the input buffer. So from initially we have a buffer with the entire text from a file, right? So if you think about it, we made sure that this pointer is not allocated on the heap and it's a new copy from a string, but it's actually straight up the string from the initial buffer, right? So that's the idea. Now the only problem with this right here, when we emit data, if you remember, I said that emit data, or I guess data structures, create their own functions. So for example, it's going to be function ivec2, which takes in int and produces an ivec2, right? And how it works, we don't really know, because you cannot implement it in stack. You have to implement it in assembly. So how it really works, it's actually here. Where is it? Right, it's actually here. You need to allocate some memory on the heap, then you need to write this pop. I guess should be a push. I don't know. I guess it's a pop from the stack, and then we place that thing that we popped on the memory. So yeah, again, we don't really have access to allocate and the memory, or I guess the heap, from the stack language itself, right? We don't have access here to that, so we cannot really implement it in stack. We have to make the compiler do this thing for us for all data structures, right? And initially that's fine because ivec2 is a name that we already have, but then comes ivec2.x, right, which takes in an ivec2 and produces an int, right? And this function as well, we don't have the meanings to implement it directly. We have to base on the compiler to do that. Well, it's like, again, we do a pop, right? But then we need a function that offsets into the memory, and we don't have that in stack, so we have to let the compiler do that. But even then, even if we had it, it's much nicer to, you know, if you create a data structure, you already know that you have access to these functions, you don't have to make them yourself, so that's pretty cool. But the problem is that like the thing that I don't really like is that we need to allocate memory to generate the name of this function. And it really sucks because I couldn't find a better way to do it. We just allocate that thing here and then it leaks. Basically we cannot free it, right? So I created these data buffs like a temporary array where we store all of these things, so at the end of the execution we can free it. But yeah, it really sucks. So maybe once we do type checking, maybe we can reuse that part here instead of this. And yeah, type checking is gonna be really interesting in this language. Like I really want to do that soon, but for now let's do if statements so we can actually, you know, use the language. So yeah, let's actually start on the if statements. Okay, so let's see. We need to add some new instructions, right? It's gonna be if, I'm gonna use then, else, and to keep it close to my other language, I'm gonna use p for the ending of an if statement. And similarly to that one, I'm gonna say that and this is mainly because we want to make it easy for the parsing. I'm gonna say that when you use an if, you have to also define the else branch. So this is gonna help with, I guess parsing is just a small part, but it should help a lot with the fact that if statements are gonna be expressions, so they return stuff. I mean, I guess in case of this language, defining the else is not really that important because the else case doesn't do anything if you don't define it. But I feel like it's a good idea to make it like mandatory to define. I guess yeah, we'll see. I mean, for type checking specifically, right, it would be interesting. So I was just thinking that maybe for type checking we can force if statements to, like, on each branch to return the same thing, right? So it's gonna be like you either return, like if you return an integer on the then branch, then on the else branch you also have to return an int, right? Because otherwise it can make type checking difficult, or does it? Not sure. I mean, we'll see if the else branch is really needed. But yeah, if you think about it, let's go into example.sl and try to create this like if statement. So here we add together two things, right? And we can say that if this thing is greater than, so we would put 10, right? And then less, because we want to check that this thing is greater than 10. So 10 is going to be the first argument and this is going to be the second one, right? So right now on the stack we have a boolean, right? And if statements should take in a boolean. If, I guess we don't need a then keyword, because we can just say that in here we do something, then else something, and then phi. So in the if branch, let's say if it's less than 10, we say 0. Oh, and another cool idea is, what if we dupe this thing? So actually we dupe it, right? So we still have the original value, and here it's like original value 10. So 10 is less than the original value. We start the if, and if that's true, then we do 0. I could also pop first, right? So I guess before the if statement, the stack looks like int bool. That's on the stack, an int and a bool. So if is gonna pop the boolean, but we still have an integer, right? So that's that. And then we also pop the integer, right? We put 0 on the stack, and here we don't do anything because we want to return int, right? So if it's greater than 10, we return it, otherwise we say 0. So that's how you would do it. So I guess in that case, else is not really needed. All right, and this is an example where each branch does something, like it returns something completely different. So for the, well, actually that's not really true, because this one takes in an int and produces an int, so it's kind of like doing nothing, and the else branch is also doing nothing. So I'm not sure if I want, yeah, like maybe it's not really required to also have the else. So yeah, let's say it's like this, right? So I wouldn't say it's extremely needed to have an else. Doesn't seem like that, right? Okay, so yeah, let's just say that if you won't be required to put the else, right? So that's that. All right, because if you think about it, the if branch is gonna be just a list of instructions. Else branch is also gonna be a list of instructions. So if you don't provide the else, that list is automatically gonna be empty. So yeah, and yeah, it's gonna be interesting to do type checking on ifs. So yeah, it's gonna be interesting. Okay, so then we have only if, else, and phi. Yeah, and this is where I said that we can add emojis, but okay, anyways. Right, so let's add stack token if, stack token else, stack token phi, and that should be everything, right? And now we have to also add them here. So stack token if, we just return if. For the else we do else, and for this one we do fee. Okay, oh, that makes sense. Now let's go into the stack Lexer next. So we have to add the tokens here, and we have to add them actually at this place. So it's gonna be something like data. I mean, it's not that complicated. So we want to check with slice if. Oh, we already have it. Nice. Right. If we find the slice if, then we return a token if. We don't really care about the actual value because the actual value is an if. So yeah. Oh yeah, and maybe something else that I added was this stack token constructor, which I guess it's ugly, but it makes you write less stuff, so maybe it's better. I don't know. We'll see when the compiler will fail with some weird error and realize that, oh shit, that's not that good. Anyway, yeah, so we have these keywords, right? We now have the keywords into the Lexer. So if we go into tests and create a new 07 if.sl, we can just put the tokens and see if, oh, it's, yeah, true if 0 else 1 fee, right? Like this would be how you do it, right? I have to get used to the fact that first it's exactly like this thing, right? If you think about it. Ternary operator. Yeah, and I mean in ternary operator you have to use, but yeah, I guess. So let's try to build. I think it's gonna fail because we don't. That's true because yeah. Let's do tests 07. I have to lex it, right? So it's gonna do if else fee, right? So you can see the list of instructions. Instruction it's 0, 1, and so on. And we could even have stuff like this. You don't have to do only one thing. You can do more stuff. Let's do it like this. Let's do this test like this, right? So here is the list of things you can actually do. So let me just add 07 if.ref, and this is gonna be the test. So yeah, I don't remember if I did this one, but I just added some scripts for doing checks, right? Like running the tests, but that's not that interesting. Anyway, let's go back. So we added the tokens and we are able to tokenize them. That's nice. And also print them, which we didn't change anything here, which is pretty cool. But now let's see example actually. So here we have the if statement, right? We have the if statement. So what would happen if we actually run this thing on example? Well, we tokenize it, obviously. It's yeah. But what would happen if we try to parse it? Expected end got if on line 15. Wait, what? Line 15, 12. Yeah. Not sure why it says 15, 12. Like, why does it show the previous character? Maybe we haven't. Why does it say the previous character though? Like, it shouldn't. It should say 16, I guess. Like 15, 12, right? It's something broken, maybe? Is it something broken? I don't think so. Yeah, I don't know. Maybe it's something broken in the thing itself. I have no idea. But we'll see. Because here we put position. Like, position should be fine. It should be the start, right? If I remember correctly, position is pause, so it should be fine. Yeah. Anyway, let's continue with the parser. So, some errors, like this is the part, so stack show error, where we generate the line and column. So something could be broken in this one, but I mean, I set them to 1, so that's weird. Anyway, like, what if I do if at the beginning? Is it gonna say 1 1? Yeah, it says 1 1. What if I do it here? It's gonna say 2 1. 125. Okay, so something's broken. Maybe in this one. Maybe it should be like this. Yeah, it's actually like this. It should be less than equal, right? 15, 12. The fuck? It still says 15, 12. Ah, because I forgot to compile it. Yeah, but 15, 30. Okay, now this is interesting. Yeah, like, I would say it should be less than equal, obviously. But not sure why. Yeah, I mean, I don't want to waste too much time on something like this, but that's weird, right? You know what? Let me just do this because it makes easier navigation. Okay, so yeah, it's weird, but we don't really care about that. It's yeah, not important. We want to add actually some new expressions in our stack AST. So let's do stack AST expression if, right? So this one is going to be like this. And what's going to be the idea here? It's not going to be just a node. It should be, as I said, 2 lists. One list for the if and one list for the else, right, with all the instructions. So how are we gonna do that? Well, we can create a new typedef struct, and this one is going to be stack ast if, or maybe even conditional. It can be called like conditional expression, I guess. So as I said, this one should be ds dynamic array for the if. I could say if like this, and this should be stack stack ast expressions, right? In this list we store stack ast expressions, so you can even have nested ifs, I guess. And the other list, dynamic array else, I mean, I could call them ifs and elses, but it's weird. I don't really know. It should be the same thing, right? And now here we have stack ast conditional con, and yeah, this one is going to be interesting. Maybe we can have a special parser for this one. So for example, yeah, here we do default, right? Right, so in case we find the token if, right, then what we want to do is gonna say, okay, this is valid. First of all, let's just add return defer, but I'm pretty sure we also want a function that parses the if statement. So stack parser parse conditional, and here should have stack parser stack ast expression. Oh, I should just pass this, right? So that's the function. Now actually this thing can return an error, so I should return defer its value, actually, probably. Yeah, I think this is how you actually have to do it. Yeah, I mean, sure, fair enough. We could have used like some grammar generators for parsing, but I think it's more fun to do it from scratch, even though we don't have proper error handling, right? Like if you get an error, you saw here, it's just bad. Like syntax errors are gonna be the worst to actually implement them, but it is what it is. So we are gonna hope that the user of the language kind of understands the syntax, so they don't have too many syntax errors. And even when you have syntax errors, maybe like just checking the first one is gonna be enough to figure out what happened. So yeah, okay, so let's implement this stack parser. So let's do it actually here, right after the structure. So we are gonna call it parse conditional, and we actually need a reference to the thing, so we have to do it here. But maybe maybe I'm gonna do it like this thing. Instead of parsing an expression, it parses the conditional, right? And then we initialize it. So I think that's right, like here stfunc. That could be an idea. Yeah, why not? Why not? Let's just say that this thing actually parses a condition instead. So now if we go here, we can say that maybe we have something like stack ast conditional con, and maybe we initialize it with 0. Sure, we need something like this, I would say. All right, we initialize it, and then we need to parse. I mean, we kind of need to parse this thing, but here we pass the condition, right? Like that would be the idea. And then we can have a define like this for cond, and here we need a conditional expression cond, and then cond is equal to that, right? So we can actually use something like this. So expression is expression cond, and here we can just say wait, what? Oh, yeah, shouldn't really be, we'll just say node. Right, so we can't say that, obviously, but we need to maybe have here like, if this thing is not 0, then we return differ 1, and here return differ 0. So we could do something like this. I think that's better because now this function only parses the condition, doesn't have to worry about anything else. Okay, so for that we can actually make use of the other parsing functions and just copy paste stuff from them. So yeah, like here we define the result. So it's going to be parse condition, right? First we have to read a token, and we have to make sure that the token is a fee token. And here we say, okay, we expected a fee token. Wait, am I low IQ or what? We should have an if token. Yeah, thank you for reminding me. Okay. And now after the if token, which I guess the if token is like, you actually have to have it. Cannot really not have it, but yeah. We need a list of other tokens now. So let's try to find that. So it's not gonna be, could be a do while, like it could be a do while. And why is that? Why could it be a do while actually? So at this point now we are searching for the else, right? For the else or for the fee, right? One of the two. We need to find the ending. So we are going to read a token, right? And if that token is somehow else or fee, see, like this is the point where it kind of sucks. Yeah, so you can even have something like this in the language, right? Something that doesn't do anything, but like who would do that though? Like that's weird. So I would search for the fee or for the else in this do while loop. maybe we can even have similar thing like parse nodes, because we have two lists with the same stuff, right? So we could have something similar to this function to help us, but it's not really that great though, because they look different. Okay, so let's see. So we have to cover all the cases, right? We have to say that in this case, yeah, let's try to reuse this function, because parse nodes is a bit more helpful than what we have right now, copy pasted. So, right, we found an if statement. Now, if we find an else statement, actually we can say that, I mean, as I said, if statement, else statement is kind of, you can have it or you don't have it, it's not that important. Right, so yeah, let's actually say, I guess at this point, I mean at this point maybe a do while makes sense, actually do while true. So here we are gonna try to pick the parser, right? And if we don't have a token name, then we should stop, right? So we found an if statement, and now we are gonna try to search for something else. And I guess that something else is this. I mean, this condition looks a bit ugly, so I could even just do while token.kind is not equal to stack token name, or I guess while it is equal. And while it is equal, we actually token, we have to read that token that we picked, and I just do to do add to if, right? We add to the if list. That's the idea. And once we find something that's not a name token, we have to check, because now we have two cases. Either is a fee or an else. If it's a fee, we can actually just stop with everything. So let's do that. So let's say here, if we find a fee, then that's the end of the if statement, right? So we can just stop. We have to read the fee as well, but we stop. Then on the other hand, if we find an else, we know that we have the same thing like here again, but this time for the else case. So we do the same thing like here, but it's actually for the else branch, right? And now if we find something that's not a name, but see, here it's kind of ugly, because if we find another, oh shit, yeah, if we find another if, for example, in the so it doesn't really work like this really well, because if we find another if statement, then we have to parse it. But see, at this point becomes kind of complicated, because let's say we have something like true if something and then fee, and now let's replace this 0 with something like false if 0 else 1 v. I guess it's maybe obvious because you find if, then you find else, and then you find v. So maybe it's not, yeah, maybe it's not that hard actually. But first let's do it like this, only for names, because it's gonna make things a bit more, wait. So here we want to show something like expected at some point. So now we found something that's not a name, right? And we have to check that it's actually an ending token. So let me just go to parse function. And let's say that, I'm gonna do something like if the token kind is equal to phi, in this case, we parse it and that's fine. We just go next. Oh, but this is if. And on the else case, if we don't have that, we just have to show the error and return before 1, right? So let's just say that if statements are going to be something like this. You read the if, right? And then you have to read names, but we'll have to change this one to be expressions actually. So you have to read expressions in this at this point, right? Then you can either have a phi after all the expressions, which can be actually empty. You can have a phi that just stops the entire expression because it's the end, or you can have an else statement, and this else statement is, you know, acting like a separator between the ifs and the elses. So you find it, you read it, and then we go next and we pick. And at this point, if we find like a name, we keep reading it. And then here we check for the phi. Alright, so that's how this thing is gonna work, right? I'm pretty sure this thing will be placed like somewhere here, because we are gonna need expressions inside of this. And maybe like now, like this one is gonna be defined like this here, because we are gonna need it in multiple functions. So it's like function in function or something. So yeah, anyway, so right now this thing will work kind of. So if we go here, right, and let's do a function. Let's do func. Let's do it like this because we don't really care about type checking now. Function, let's name it star star star. When is this thing gonna work, right? So it's gonna work if I do something like this for now, right? We have name here and name here. Let's build. We don't, yeah, let's also fill in the other stuff. So for example here, case stack st expression cond. We have to stack st free, stack st condition free, and break. So let's implement this function. Let's go to our conditional st condition free, and what this thing will have to do is, oh, and this is pretty funny. We also need to define this one on top, like here. And I guess we cannot really, we have to do it in the same place, so yeah, it's fine. Let's go here and let's say, okay, this one is break. So what we have to do is two for loops, unsigned int I. We have to free each expression, obviously. So stack st expression free, and here we need to pass in the expression. So I'm gonna do I guess I said we are gonna have pointers, so let's do expression like this. And here we have stack st expression. First it's gonna be 0. See, but now I guess I have to do it like this. And then ds dynamic array get ref. Right, I might have to do it like this. So yeah, I was just thinking that in the dynamic array we are gonna store stack st expressions, so the entire structure, and we basically copy that thing into the pointer. Maybe it's gonna, I'm not sure, it's just extremely weird, but right now I cannot think about freeing stuff in. Not sure why, but we free those, right? And now this dynamic array free, and we just free the dynamic arrays. Yeah, it's a bit weird, but right now we haven't put anything into the dynamic array, so I don't know how it's gonna look like, but I think that's how I want to do it. So in the dynamic array we are gonna put stack st expressions, so this data structure, right, with kind, number, st node. But I mean, it doesn't even matter if you think about it, because yeah, we don't allocate anything. I lost it, but yeah, it's here. So I guess that's fine. Hopefully we'll see if it works or not when we do the free, but let's try to build again. So next build, it's probably gonna fail for printing or something. 781, yeah, for printing. So okay, so in this case we actually have to do different stuff. So it's gonna be here, 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 but for case stack st expression condition, let's just break for now, and maybe let's just print f to do print condition. Right, so we print the condition. Right, what else do we need? 1511. Oh, so emitting the actual if. That's gonna be interesting. And now we should be okay. So if we try to parse, stack parser parse condition. So what happened? So it says on line 14, 11. Excuse me, what? Expected got boolean. Huh. Really, did I make a mistake in this one? Shouldn't have, like, what? Guess I put something at some point in here and I don't see it, but I don't know exactly what. So 29. Yeah, like it's so broken. Expected data got number. Huh. Let's just delete. Okay, so it works fine. But it was just because I put the if. Really? Okay, so if kind of works if I do it like this, probably. No, it doesn't want to work. Okay, so show expected, maybe. Oh, show expected 1 should be right. Show expected 1. And here we need to say the. Wait, isn't it defined? Show expected, okay. Expected fee got number. Haven't I? Okay, so if it's a name token, oh yeah, okay, fair enough. It's because I said the name here instead of all the other stuff that we can have. So here you can see that. Yeah, let's try to actually implement the right way of doing this. So here we need to actually do a do while loop, do while true, and at this point we have to pick the parser, right? We have to pick, and if token.kind is equal to stack token fee, then we have to do kind of this. We can just stop. If we find else, again we read it, but we just break. Right, and in any other case, we have to somehow parse expressions. But let's just say add to the if, and we just read that token, we skip it, and yeah. And now we have the same thing again. We have the same thing again, and this time we try to get the feed token to stop, but we no longer have the else branch. Right, and we might have, like when we are gonna parse expressions here, maybe we can find errors like that, right? Okay. So now we actually parse something. Okay, let's try to, so here in example, you see we have 0 and 1. So let's try to maybe parse expression here. So how is it gonna work? Stack parser parse expression. Right. Well, maybe the first thing let's initialize the conditional. So dynamic array init condition if, and it's going to be size of stack as the expression. So we are going to store expressions. Okay, so we store expressions in this thing, and let's see how this thing is going to work. So we are going to do stack parser parse expression, parser and expression. We don't have expr yet, so maybe we need stack as the expression. We parse the expression, and here it's gonna be also like if it's not 0, then we can show some kind of expected error, or maybe we just return defer. No, let's just say we return defer. We don't show any extra errors. Okay, so we parsed the expression, and now we have to add it. So this dynamic array append to our condition if and address of expression. And I mean, if this thing is not 0, we just say, out of memory. Okay, so that's how we do that. Right, that's how we add the expressions in the if. Okay, let's see if it still works. Like if it's not gonna, break. Oh shit. Expected end got if. I guess we need to, so here we picked, no. It doesn't make sense. What? Expected end got if? Like what? Because here we read the if, so it's actually gone, and at this point we have the 0. So we try to I guess this thing is extra now. Yeah. Let's see. Still does something, so that's encouraging, you know. Like, yeah. So let's replace all of this, and here we put it into the else category. Right, so I would say, you know, it's the same thing. This one should still work. It does something at least. So yeah. Fair enough, like, it doesn't really matter. This part is just parsing at this point. We do it however we manage to get it to work. That's something. So let's try to print the condition. Stack st condition dump. So here this thing might want expression dot cond, so the condition file std out. I guess it's like file pointer std out. Oh, I mean it's std out. Yeah, it's std out. And maybe the indent. Indent times 2. Stack st condition dump. So that's gonna be that. Oh, and even this function is gonna be needed up top. So here, but it's gonna be just expression dump, and it also needs unsigned int indent as the expression. So we need to implement this function at some point. So maybe before the free. Yeah, maybe before the free. So wait, where is the dump? Here. So expression dump is gonna be just basically this part. So stack st expression dump probe std out indent times 2. Oh, I guess expression. So that's gonna be the actual thingy. All right. Yeah, and we don't really have expressions in other places, so that's that. So we have expression. Yeah, I mean, I could have just sent the thingy, but I don't really care. And string slice, it's only needed in some cases, so I might just, oh wow, might just do something like this. So ugly, dude. Oh my god. I need a C formatter. Anyway, so we kind of do all of this, which is what we actually need, right? And now let's do conditional. So conditional is going to be here, condition dump. So condition dump. All right, and how this thing is going to work is, let's fprintf stuff. So I would say here is going to be just the indent, right? So that's that. And how are we gonna do this? So here I want to print maybe an if like that. We don't need anything. We just put indent. Right. And oh my god, and signed int I is equal to 0. I is less than condition.if.count I plus plus. So we need to print all of those and also all of the else cases. And yeah, if you think about it, ifs and else's are just expressions. So you can just say stack st expression or equals to 0. And then we can just say stack st expression dump. And I think I want something like define indent increment like 4 or something. So instead of doing times 2, we can just say plus indent increment, because that's pretty ugly. It's gonna be really ugly with times 2 everywhere. So now when we call this function, we just actually add the increment. So where is this thing used now? I guess then it means that we don't want to do plus at this stage. We might want, yeah, I think it's fine like this. So indent increment. Yeah, I think it's fine. Here we increase it, right? So that's that. Okay. And we need to take it from the dynamic array. So dynamic array get condition if I and expression address. So stack st expression dump is gonna take expression std out and indent plus indent increment, I think. So let's do the same thing for else, and let's put the else and the field. So I'm still gonna print the else even though it's empty, for example. Don't really care about that. So yeah, so that's gonna be this case, right? And here we increase the indent. That looks fine. let's try to build it. And now let's try to run this. So holy shit, you can actually see the if else. That's nice. Let's try to do a more complicated if else, if you'd ask me. Let's do function star star star. Let's say it takes in an int and doesn't return anything. Like that, and maybe on the else case, let's do like true if we like 0, and here maybe else. Oh, we already have the else, right? So let's see if this thing actually works, because this one is like a more stressful test. Okay, and it still kind of works, right? So if we have the 0 case, and then we have a big stuff here, and then yeah, it looks like it's actually working. Yeah, what if we say here we don't have any, yeah, it's still, yeah, so it wasn't like, I don't know what the error was, but you can see the if is actually nested properly. And even if here we say like 1 2 3, it's still gonna work, right? Yeah, and see, it's like a bunch of instructions, and I mean instructions can actually, I don't know, be even calling recursively or stuff, right? So imagine like the if case is actually calling recursively the function, right? And the else case is actually the base case that stops the recursion. So in this way, now we have loops in our language, right? We have defined the loops. Obviously, I still kind of want to have the real while loops, but we'll see. So that was everything for the ST, I guess. Let's just check Valgrind. I'm curious if I freaked anything up, so it doesn't look like I did in this way of freeing stuff. Right, so I think it's fine. I guess that's how I usually do it, right? So if I put something into the dynamic array, when I want to free it, usually I remember I use getref, but it's been quite a while, so I don't remember if I'm doing it right. But I think that's how you have to do it. You have to get the reference, and yeah. So that's kind of it for the ST. Let's just see again. So we just added, let me just find it because it's really messy. Like having a single file, honestly, it's better in my opinion compared to when I did the other compiler with a bunch of files. I think this one is much nicer, only one file. But yeah, we added this conditional, and the conditional is an expression, right? It's also an expression. And how it works is that we have an if branch and an else branch, and in each branch we put expressions, multiple expressions, which obviously can be recursive. So yeah, now the language becomes a bit more deep, we can say that. So yeah, that's the first thing. And yeah, parsing, I mean, I guess, you know, if you want to do it properly, you should use a grammar generator, but kind of like trying to figure out this part. It's quite entertaining, I would say. Yeah, so we parse the expression, and then we dumped the conditional, and also refactor this one just to have dump here. Right, and we also have the free, which I guess it's fine. Not 100% sure yet, but looks fine. Then we have the function which we didn't change, but we copied from it, we copy pasted stuff. Stack.st dump, we changed it because we needed to have the expression dump now. And stack.st free, we don't need to do anything because it's being called. Here, ifs are not functions, so we don't need to worry about that. This part is the type checking that I'm planning to do at some point. So context is actually gonna be the list of all functions that we have, all functions that are predefined, like ivec 2.x. If you define a data structure, we want all of those to be in this context so we can do type checking. And as I said, we maybe can use the names of the functions from this context in other places. But the type checker, it's gonna be kind of interesting. Like, how are we gonna do the generic types? Because dup is kind of generic, right? It duplicates any item. Doesn't have to be an integer. So how are we gonna do that? Maybe with inference, right? So in that context, maybe a is an int, so we just say int. But then what about functions that are completely generic, like even the input is generic? We'll have to see how we can actually like allow generics. And I was thinking about, but maybe it's a bit too difficult to have like traits or classes from Haskell, like AQ compare. That would be kind of useful, but I think it's gonna be like a long way if we want to add these things. Like, probably not right now, but I think like allowing a generic type might make sense, but we'll see how we can do inference there, because that's gonna be, I think the type checking might be the most interesting part of this language, in fact, because like being able to type check this shit, like that would be quite fun. So and now for the assembler, for the AST, I think I mean, where is it? I was just thinking that maybe we can just refactor some of these, like for example, things that we always see used in functions into like emit pop, like this part. But not right now. I just want to do the if statement at this stage, but where did I put a to do comment? Emit the if statement. So let's just have something like stack assembler emit expression conditional. Right, and let's see, so where did I put this one? Okay, I guess I can just reuse something like this. Stack assembler emit conditional st cond. So I don't think we have time for this one, unless it's pretty easy, but dump cond. Wait, isn't it on dump or something? Yeah, I just wanted to copy paste this part in here. So yeah, we get the expressions, right? And the expressions are gonna be kind of intuitive. What we are gonna do with them, we are just gonna emit the expressions recursively. So yeah, like that's kind of intuitive, right? We need emit expression to be defined first. So like that. Oh, it should be static, if you'd ask me. Right, it makes sense to be static. Where is it used? It's used in assembler emit function. Yeah, so it's exactly the same thing as here. We just emit the ifs, right? We just emit the if statements, and here we just emit the else statements. But you know, that's not, I mean, would be enough if we go to example and let's say, let's delete the, you know, let's actually have int and it returns an int. And let's do something like dupe. On the if case we do 0, on the else case we do nothing. So on the else case we just return the number. And let's do 1 star star star. So this should say 0, right? Like that's what we expect. And funnily enough, it's gonna say 0, right? And if we say 11, yeah, it's also gonna show 0, right? Because this thing is in order. But I mean, we could force it to say 11 like this. Really? Why does it show No, like this is quite interesting. So yeah, because we don't consume this guy, right? Like what happens here, because of what we did right now, is that we just put the expressions like that, right? So we just list them. You can see here we put 0 on the stack and here we call pop. So we could do, if we do this thing, it's gonna say 11, right? Because right now it doesn't work. But this would be the actual minimum function. Let's do, so this should say, yeah, right now doesn't work, but yeah. So let's make this one work, and then we'll come back with the to do here. To do actually implement. So usually we do something like, so in assembly, right? Let's do a comment. Let's do a comment. So in assembly, right, we are gonna have something like a true or a false in Rx, let's imagine, right? So we can use compare and like test to figure out if it's true. Then we have to do a jump true or something. I don't know how it's called yet, I haven't looked, but we have a jump true to the if and here we are gonna have 1, 2 and so on, but we jump to the if label, or I guess it's gonna be, yeah, I mean it's if, right? If it's true. And if it's false, we have the else label, and here we have fee label, right? And here it's unconditional jump to fee. So here we put all the stuff from else expression, and here we put all the stuff from if expression. So that's kind of the structure of our if statement, right? So yeah, it kind of makes sense, right? But we have to put some labels on the ifs because we might have multiple if statements in a single function, and this dot in the beginning, it means private labels, so they are available only in this function, but you can still have multiple ifs in a single function. But let's try to maybe hard code this thing for now. So I'm gonna switch them around. Let's use emit for emitting stuff. So I guess labels should start at the start. So it's gonna be else, right? And as I said here, we are gonna have if, and the other cool thingy is gonna be a jump. So let's do jump to fee, I guess dot fee. And yeah, again, we need to add the real stuff, so fee. All right, so we did this part, then all the instructions, jump, if, fee, right? So that's basically the if statement. And now we need to do the test and jump if true. So what I'm gonna do, because I don't really remember on top of my head how that thing worked, is in emit don't really remember how we did, like it's probably like test jump if true. Yeah, jump if true. We need to test rax. Oops. So that's this part right here. So let's actually copy this. So we use test. I guess test does some kind of XOR, so that's the idea. Oh, okay. So we test rax, and then jump not zero. Jump not zero is the jump if true, basically. Jump not zero to if. Yeah, I think that's it. Jump not zero to the if label. And yeah, as I said, here we'll do like if one, if two, and so on. Like, but that's kind of it. And before test rax, we need to actually pop the value from the stack. So we need to pop a boolean. I mean, it doesn't matter what we pop, it's like boolean. Where do we have something like this thing, for example? This thing is actually popping stuff from the stack, so we just put this thing here, and yeah, so this thing is gonna pop a boolean from the stack. You know, we assume it's a boolean, like that's the point. We assume it's a boolean, we get its value into rax, then we test jump not zero, and if it's true it's gonna jump here, and if it's false it's gonna fall through the else and then jump to the end. So that's how we implement, but we have to actually implement it because what if we have multiple if statements? We want to have a mapping, right? So add a mapping for the ifs, because if we have multiple ifs we need to somehow count them, right? So right now it only works with one if per function, but Okay, let's go here, let's build, and let's check what happens now if we run this. So first it's 0, right? It's 0. And what if we put here a 9? It's a 9. So am I wrong with this? I mean, order of operations, it's still messing up with me, but so yeah, on the stack we have a 9 because we dupe it, and then a 10, right? And if we apply less than, it's gonna be 10 less than 9 basically, right? So that's false, and it goes to the else case. Yeah, and on the else case we can do stuff like else 1 IVEC2, and then let's call exclamation points, right? And it should say 10 right now, I think. Yo, it just works. And what if we have something like, let's do a for loop that does something, I don't know what though. So let's say 1 plus, and then it calls again to itself, right? We don't really have printing, so it's gonna say 0 because it worked. All right, even if we put here 1, it's gonna say 0, right? Because after some time it's gonna do that. Yeah, it's really annoying that we don't have a print yet. That would be cool. So yeah, maybe let's try next time to add a print function. Like maybe it's gonna be, you know, out, int.out. So it's gonna be out. Out is gonna be a function that prints an integer. Yeah, because I don't have time right now to finish that, but that would be a nice goal, I would say. And yeah, so next time we'll finish up the ifs. We'll make a mapping for them, and we'll also add the out function. So right now, how I think it's gonna work is you call dupe, call out, then you do the if, and it should print from 1 through 10. Right, so that's the idea, but now it doesn't work because we don't have an out. So, you know, out function is probably going to be int, doesn't return anything, and yeah, right now doesn't work, but maybe we'll be able to implement it. So yeah, that's the goal. Yeah, so maybe we could add strings first, but I think out is an important function to add right now. So yeah, I think that's what we are gonna do next time. So we do implement out. Obviously adding like a syntax highlight for Vim would also be nice, but let's not worry about it. So yeah, we'll fix the ifs to be able to have multiple ifs. So yeah, I mean, it doesn't even matter. We already know it's not gonna work. So yeah, we are gonna add more labels for if statements and actually implement out. So yeah, hopefully it makes sense how the if works by that explanation, right? We just check if we have a true on the stack. If we have a true, we jump to the if label, which is here, and we do all the expressions. If we don't have a true on the stack, we fall through the else, we do all the else expressions, and then we jump to the end, unconditional jump to the end, right? So that's how if works. And I mean, even if we check the assembly, right, you can even see it here. We test if it's true. If it's not, we do the else. If it's true, we do the if, and then we jump to the end. And yeah, you can actually see that we need some kind of labeling for ifs in this point, because if you have nested ifs, doesn't work at all. If you have more than one if, won't work. So yeah, that's the goal. So yeah, next time let's fix this issue and also add the out function. So let's see in the next one.